Go ahead. So as we travel around the sun, keep going, this is going to go fairly fast. I got a bunch of slides, so I'll cover this quickly. 50% of the energy from that comes from the sun hits the earth and gets stored here. So that gives us a constant temperature wherever we're at. That's where the energy savings comes from. We use water as the means of transporting that thermal energy out of the earth into our buildings. This is a buildings technology for the most part. I've done some process loads for industrial applications and things like that, but for the most part, most of the energy for, there'll be another slide. No, the other direction. Forward. Yeah, forward. One more. Let's see, one more. Keep going. There it is. Okay. 43% of the carbon emissions, 39% of the primary energy consumption, 71% of the electricity in the U.S., 53% of the natural gas. All that energy is used by buildings. So the building market is even bigger than the transportation market as far as consuming a lot of this stuff, where the solar produces it. What geothermal does for a building is that we tap this earth, this solar collector we have that we live on, for that constant temperature. And I'll show you here in a couple more slides what that means to us. Go ahead. One more. So here's the basic principles. You've probably heard the term heat pump. It's a matter of pumping heat from one place to another. Heat's removed or added from something. That's how all of our air conditioners work. We pull the heat out of the building, making the building cooler, and we either take that heat outside, compress it, raise its temperature, so we can discharge it to 100-degree air when it's 100 outside, or in some of the big buildings like this one or all the downtown buildings, we put it into water and we evaporate the water to get rid of that heat. So the further down we take this temperature, the more energy savings we get. That's why you see large buildings with evaporative coolers or cooling towers on them, is because you're going from a dry bulb, which we all feel, like 100 degrees, 98 today, something like that, to the wet bulb, which you'll see the weather forecasters talk about percent of rain. 100% chance of rain means the wet bulb and the dry bulb are the same temperature. So the wet bulb will always be lower than the dry bulb, so if you can evaporate water, you get down to that wet bulb. So you can gain, if it's 98 outside, it might have an 80-degree wet bulb, which at wet bulb, that's the temperature at which the water in the air falls out or rains. So when you get down to 80, that 10 degrees can be 25% savings on your energy bill. When you go to the earth in Houston, where we're 72-degree earth for the most part around town, you're going to gain another 25% energy savings. So if you flip from geothermal, from air-cooled equipment like we use on our homes, to geothermal, you're going to cut your bill in half. And it's all because you're dropping that temperature that you're trying to operate from. So you can see here this map on the right. Instead of using 99 degrees outside, we're using 72-degree dirt. So in the upper left, you're looking at a commercial building. Most applications use what we call vertical heat exchangers, and I'll show you all the different types. But we're building a heat exchanger. It's a whole bunch of parallel pipes down in the earth. We can go as deep as we need to go to achieve a thermal mass, whatever we need for that building. So if that building might be 100 tons, which might be roughly 60,000 square feet, then you need 60,000 square foot of earth, surface earth, going 300 feet deep. That's roughly kind of a metric. If you want to go 300 foot deep, then the amount of square footage that you have to air condition is how much square footage of soil you need to build that heat exchanger in.
Could you repeat that metric one more time? Square feet of building?
Square foot of conditioned space. So if you stack it vertically, you need that much square footage of soil on the surface.
Assuming 300 feet.
Yeah, assuming that you're only going to go 300 foot deep.
Twice as far than
Yeah, if you go twice as far, you need half the area roughly. There's some other metrics that change because we went deeper.
That's the rule of thumb.
Yeah,
So you're talking about twice as deep you need to drill
right.
in order to,
Reduce the area to half as much. So if you don't have the land, like, we're not gonna do it in downtown Houston.
no,
There's
no,
just
no,
not
no.
enough land for how far we've gone high.
I'm listening.
But for a library, for in your case city.
I'm a driller, so.
Okay. So the amount of land that it takes to drill on top to maneuver this rig is equal to the square footage that the building is trying to air condition.
Is that distance a function of the wells not sharing heat or isolating? Are you isolating the wells? Is that why you need so much?
No, that's the thermal mass that it takes. Now the distance that you put those loops, I'm gonna call them loops, the plastic tubes that were shown in that picture, the distance apart those are is based on the imbalance between the load profile of the building. The thermal mass is still the same. How far apart you put them is based on how imbalanced your loads are and how conductive the soils are, how fast heat moves in that particular soil. So it could be anywhere from, a long time ago, they were 10-foot centers, 20-foot centers, 30-foot centers. In some parts, if you get a totally imbalanced building, you get 60-foot centers.
Any particular soils that you,
No, not really. The higher the density of the soil, the better it transfers heat, but the more it costs to drill. So typically, from a capital standpoint, it's about the same cost per ton if you wanted to use ton as a metric.
Can you use the rule of thumb of 1 well per ton?
You can use that. That's
a
a,
lot of people understand.
yeah, that's a metric that a lot of people understand. More to the equation, but that's a good rule of thumb.
That's 300 people.
Right. Yeah, for a typical office building or house, if you've got a data center, it's gonna probably be twice that, because you're pumping in a whole lot more heat than you're taking out coming off the computers. So, you see here that the earth is 72 degrees, the building is 74 degrees. The bigger the temperature difference that you're trying to bridge, the more it costs you to operate. So the higher the delta T, the dollars operate. Go to the next one. So by going from a 74-degree building to a 72-degree earth, it'll cost half as much as it would going from a 74-degree building to a 98-degree air outside. One more. Now in the winter, see what the earth did? All summer we pump heat into the earth. It's a big storage vessel like a battery, except this is a heat battery. Instead of storing electrical charge, we're storing heat. So we warm the soils up. Now when we go into winter, the same heat we put in June is still there in December. So we pull that same heat back out and put it back in the building. That's why it's called a renewable technology, is because we're not burning fuel, we're not burning anything. We're taking heat that we gain in the summer and storing it for reuse in the winter, or reuse for domestic hot water in the house, heating swimming pools, all kinds of process heating applications.
You can actually make that much difference. The heat that you take for the summer to put it in the soil, or you're going to actually warm the soil up.
Yes, and you can go farther than that if you want. Like in Canada, they take hot water solar panels and pull the heat in the summer, put it in the earth in the summer, so that they can ride out their winters. There's a lot of that going on in Canada right now.
And then come February or March, your soil temperature is going to be 72 again, so you can start heating it up again.
If that's what your parameters are that you designed to, you can have it fully depleted by the time you're ready to start charging again.
Well, because you'd be in a bad shape if your soil was 80 degrees at the start of summer, right?
It's still
better than 90.
Still better than 90 degrees, but yeah, it's not as good as 72.
Right.
Yeah, whatever the temperature difference is, that's what you're going to pay to bridge. We call it bridging.
Is there any?
you're probably going to take us there.
Yeah.
I'm just trying to think of like how I would apply this at home in a real simplistic manner. Maybe your slides will take us there.
Yes.
How do you want that? You know what I mean? I understand the philosophy behind all it. But how I could take this home in a little package, not a commercial package, how am I going to do it?
Well, like, Westview's full of it, River Oaks is full of geothermal. There's homes all over
I know, but
Houston.
little packages, how, like, I'm not going to go out and dig my soil up and see what temperature it is, you know. What packages are there around that you do?
Basically, I think enough land is what
Yeah.
the restriction is. If you live on a small piece of property, there's not enough land to do the drilling that you need to do, but, you know, in some areas where you have enough land around the house, I think it's practical.
Yeah, you can go under the driveway, in the front yards. It doesn't take much land, because most houses don't require much tonnage.
Okay, I just need to sell this stuff, so I'm trying to
Okay.
take all the information I can get, thank you.
Yeah, the
Is
drill,
there any damage to the soil from heating it or cooling it from changing the temperature in the soil?
depending on what your soils are and what your heat profile looks like. If you've got limitations because of the soil type, then it'll change the design of the heat exchanger. But you can get it where you swing the earth only a couple degrees.
But Greg, it doesn't make anything toxic, right?
No.
Right.
Yeah, it's strictly heat. All it does is warm the soil, sands, clays, rocks, whatever it is.
Yeah, and most of the thermal effects are very deep. You know, the surface part is probably about this deep. You're worried about
Yeah, you
what's
see
going
the
to grow or not
insulating
grow.
layer?
So this is 300 feet down.
I'm gonna say that insulating layer in Houston's probably 8 feet, maybe. So that top 8 feet, we call it an insulating layer, but that top 8 feet is affected by what happens in the summer. It gets warm, in the winter it gets cold. Kind of like a wetsuit. Once you get the water into the material and it holds it still, it becomes an insulating layer, and you can be warm in cold water. That's kind of what that top layer, the top 10 foot of our soils is an insulating. Once we get below that, it's constant temperature year round. What happens above ground in the atmosphere, in the air, it doesn't matter. The soil never sees that once you get that deep. Okay, keep going. Yeah, we're going to run out of time here. Keep going. We'll go quick. So the geothermal heat pump's using all this land. You bring the water, you see the water circulating into a geothermal unit. I'll show you a whole bunch of different kinds of units. You see the ductwork comes off the top. I think hit the picture one more time. One more. Should be some air come. There we go. So in the heating mode, you're pulling the heat out of the water, putting it into an airstream, blowing it through your ducts, and it comes out the grills just like your current system does in your house or any other building. And in the cooling season, you pull the heat out of the air, so cold air comes out the grill, and heat goes down in the ground, transferred into that water and carried to the soils. Keep going. Keep going. Slide fills up. There we go. So roughly, you're looking at, in heating mode, 600% efficient. You buy 1 unit off the grid, the electricity to run the compressor and fan. You pull 5 units of heat out of the earth, and that yields 6 units of heat in the building as heat. Keep going. So let's look at it here from dollars. You're buying $1 off the grid to run the compressor and fan. You're pulling $5 out of the soil through that red and blue line, and you're putting $6 into the house as heat. Go one more slide. One more. There we go. So in the reverse of that, in cooling, you're still buying $1 off the grid. You're pulling $4 out of the house to make the house cold, and you're putting $5 into the earth. So you have this cycle that keeps going.